Welcome everybody to today's seminar. I know it's Thanksgiving week and all that. It's my pleasure to introduce Professor Abhay Pasupathy from Columbia University to be a speaker today. Abhay got his PhD from Cornell and I believe working with Dan Rolfe and Paul
Yes.
McKeown. And did the postdoc in Princeton in Ali Yazdani's group. And from there, he went to Columbia, I guess, more than 10 years ago. Is that the correct
That's right.
characterization?
2009. More
and
than
he,
Well,
and he's now
you're still very young, So.
Thank you.
Everything's relative.
I asked that question for fact without any connotation attached to it. But anyway, he's now professor of physics in Columbia and a group leader at the Brookhaven National Lab. He's worked on quantum nanostructures, cuprates, where I got to know his work was mostly in the context of the iron nuclides, and more recently, his group has been contributing extensively to the graphene and related Mori narrowband systems. So without further ado, Abhay, please.
Okay, thank you very much. Let me try to share my screen. So, okay, so here we go. Oh, I think you have disabled screen sharing. So you have.
Okay, so let's see. I should be able to make you as a co-host. Just give me a second. Yeah, please try now.
Okay, let's try that again. Good. I think
okay, very good.
Seeing my screen right now. I will minimize the zoom. I'll keep it around. Okay, so one thing with the Zoom is I cannot see when people ask a question, so just interrupt me anytime. So
yeah, please do, and I'll try to keep track of the chat if that happens.
Sure. Okay, so yeah, thanks, Chimiao, and yeah, so I'm happy to be there virtually and to chat with all of you about this stuff that my lab has been doing for the past couple of years quite intensively. And as Chimiao said, sort of my history is been more in the past 10 years, working more with sort of traditional correlated materials. And in the beginning, I was not super interested in this 2D field, but then I've become more and more interested as time goes on. And so I'll tell you about what I find interesting, and hopefully you find it interesting too. Okay, so let me first acknowledge the main people who have done the work. And so at Columbia, you might know that we have a pretty big group that works on 2D materials. And so I've, of course, benefited very extensively from talking to and working with all these people. In particular, I should mention Jim Hone and Corey Dean and Dmitry Basov are sort of my three main collaborators in this area. And we've had lots of theory help from the group of Angel Rubio, who's at the Max Planck in Hamburg, and my longtime collaborator, who a lot of you know very well, Rafael Fernandez. And there's sort of too many people in their groups to mention. If I put all their names here, it'll just fill up the whole page. So I'll give you a few special names at the end. Okay. Okay, good. So how do we go forward? Very good. Okay, so let me start, jump straight away into what this business is about. And this business is the business of putting things on top of other things. And I don't know if how many of you have seen this Monty Python sketch. And I'm going to play it for 30 seconds before I move on. I hope you hear the audio. And if you search for this, it's absolutely wonderful, because it tells us not only about this field, but it's a good criticism of referees, and everything else in our field is encapsulated within this 2 minutes. But let me play it for 30 seconds. So.
Gentlemen, pray silence for the president of the Royal Society for putting things on top of other things.
I thank you, gentlemen. The year has been a good one for the society. This year, our members have put more things on top of other things than ever before. But I should...
Okay, so I'll let you watch. I'll let you watch the whole thing at your convenience, but it's highly entertaining. So I still remember I had just arrived at Columbia when at the time Corey Dean, who was now my colleague, was a postdoc, and Jim Horn was explaining to me this idea of putting graphene on boron nitride and how this was going to be great. And I remember listening to this idea and thinking, man, that's one stupid idea. But Jim was a senior colleague, and I didn't want to say anything. But the stupid person turned out to be me, not Jim. And this was a brilliant idea, and in many ways has really revolutionized this 2D field. So I was completely wrong, and Jim was completely right. Okay, so let's see how I can escape from this video. Okay, very good. So one of the reasons it's kind of become such a great thing is that now the 2D materials that we can work with have really expanded since the days of graphene, which was 15 years ago. So now you have graphene, metal, you have an insulator like boron nitride, but you can also work with things that we know for a long time in bulk form, things like niobium diselenide, which is a superconductor, tungsten ditelluride, which is a 2D topological insulator. You have various 2D magnets, 2D semiconductors. And really in the last 10 years, we've learned how to use Scotch tape basically and make single layers of all of these things. And then using all of the wonderful things that Jim and company have invented is to put these things on top of other things. And that gives us, lots of new physics and lots of new advantages for experiments. One big advantage is that since these materials are two-dimensional, the field lines can sort of go out of the plane and make electrons interact over large distances, which otherwise they would not be, they would be screened. So all of these materials feature strong interactions. It's easy to shine light at these things. So optics has really had a great role to play. Very easy to make a sample, shine lasers at it and get information. And as I said, you now have building blocks that have various quantum phases like superconductivity or magnetism, and then you can just layer them with each other and sort of make your structure of choice. And very recently, I think people have started thinking about how one uses all these degrees of freedom to achieve control over the band structure, over the topology of these materials, and over the basic symmetry properties of these things. And so some of the things I'll tell you about today are in that spirit of finding ways to tune these material properties by putting things on top of other things. So there's sort of two very important reasons why I think this field has a lot of people working in it. And these are not sort of new things. These are things that were known since the time of graphene, but it's worth repeating. So one feature is if I was to translate to our traditional quantum materials language, I would call this doping on demand. So if you're looking, say, at a nictide superconductor and you draw a phase diagram like this is essentially a whole bunch of samples that's measured painstakingly, and then you assemble it together to create a phase diagram as a function of temperature or doping or whatever is your parameter. On the other hand, with these 2D materials, this axis of doping is almost trivial. What you do is you take your 2D material of choice and you have a gate electrode that's close enough to it. And by simply applying a gate voltage, you can tune the density at will inside this 2D material. And for people who worked in the quantum Hall effect, this is no big deal. This is what people have done for a long time with gallium arsenide, for example. But for those of us who work in the quantum materials side of things, this is really something that's fantastic, is you can go through your entire phase diagram with just one sample with lots of precision. The other feature that people use extensively is that you can tune the band structure of these materials by using perpendicular electric fields. So how do you do that? So for this, you need a material that is at least 2 unit cells thick. So imagine here is my bilayer material. Then you can have a gate electrode on the top and the bottom. And if you apply positive voltage to one and negative voltage to the other, then the average charge that you induce on this is going to be 0, but there's going to be an electric field that goes in the perpendicular direction between the layers. And what that will do is that will create a potential difference between the two layers, which is small but non-negligible. And that potential difference is going to essentially modify the vertical coupling and the band structure, not the coupling, but the band structure. So one famous example of that is the simple material bilayer graphene. So bilayer graphene is a semi-metal, so the band structure looks like this red scenario where you have a conduction and valence band that come and touch at a point. And as soon as you apply this electric field, it opens up a band gap, and so you convert it from a semi-metal to an insulator. And this is another sort of nice degree of freedom with which you can tune the band structure without actually having to make another sample. I would say the analog to that in the quantum materials field is something like pressure, where you can tune the bandwidth of the system without actually having to change the sample. So in my mind, it's sort of these two features that you can dope and you can change the band structure sort of as you wish, that really brings a lot of excitement and ease to doing experiments in this field. So what sorts of experiments can we do in this field? It's actually quite limited in terms of what one can do in terms of just three-dimensional quantum materials. We can certainly do transport measurements, so we can use transport to figure out what the phase diagram is, whether it's an insulator, a superconductor, or is a magnet or whatever else. This field has been a real boon for surface science techniques, which makes life good for me as an STM person, at least partly. Angle resolved photo emission is also benefited from having these essentially surface materials. And as I said, a big part of it has been optics. So you can shine light at will at these materials and do all sorts of fun stuff. And in general, what you can do is you can create phase diagrams which are a function of density, of electric field, and temperature, and figure out what the phases are. And so that's sort of the name of the game in this field. Okay, so I'm going to talk about 2 degrees of freedom, and one of these degrees of freedom is the twist degree of freedom. And so what this is basically I take 2 sheets, which are both the monolayer, and you twist one sheet relative to the other by some angle and produce a material. And what you can see, so this is sort of a cartoon version of that for 2 sheets of graphene, is when you do this kind of twist operation, you're going to produce a superstructure that's much longer than either of the atomic periodicities. And the wavelength of the superstructure is simply given by the difference in wave numbers of the 2 lattice vectors involved. And a second thing that I'll talk about, hopefully I'll have time for this, is the degree of freedom where one of these lattices is strained with respect to the other lattice. And that also introduces a lattice mismatch and gives you a long wavelength superperiodicity in the system. But let's first talk about this twist degree of freedom. So before I get into details of my experiments, let me just flash some results, which are all within the sort of last 2-year time frame for interesting results that have been obtained on materials that have been twisted in this fashion, and then doping or electric field has been applied, and the phase of the material can be changed. So the most famous of these is, of course, twisted bilayer graphene, which sort of kicked this whole business off from the discovery of superconductivity in this system. And since then, there's been sort of a huge number of experimental and theoretical works in the system that show that for this system, at integer fillings of this large unit cell, so I forgot to mention this, I should have said this, once you introduce this kind of Moiré pattern into the system, the unit cell of your lattice becomes much larger, and the unit cell is now this wavelength. And by applying a small amount of doping, so small amount of electrons per individual unit cell, you can basically fill up these large unit cells very easily. And so it's been observed that at integer fillings of this Moiré lattice, you see insulating behavior that should not occur in the single particle picture. It's for certain special integer fillings, it's also ferromagnetism has been observed with non-trivial Chern number associated with it. Superconductors have been seen when you dope away from integer fillings. We've seen some evidence for nematicity at integer filling in twisted bilayer graphene. And I put the 3 dots here just to say that who knows what else is there in this system. There might be even other interesting things. Here is a closely related system. This is a so-called ABC graphene. This is rhombohedral graphene on boron nitride. This system also shows integer filling insulating behavior, shows superconductivity, shows magnetism, lots of the same phenomenology as twisted bilayer graphene. This is twisted double bilayer graphene. So you can see that as experimentalists, it doesn't take very much imagination to do experiments in this field. If somebody has done it with 2, then you go to 3 and go to 4, and you see something new and interesting. So in twisted double bilayer graphene, then what has been seen is a field tunable, so electric field tunable ferromagnetic insulator at integer fillings. And I'll show you some evidence that we see nematicity at fractional and integer fillings in this system. There's some debate about whether superconductivity exists in the system as well, and that's a little bit debated at this point. So another interesting system.
So Abhay, what's the microscopic evidence for ferromagnetism in these systems?
So this is all from transport. So the ferromagnetism
have people seen Kerr effect, or with optics? Or
no, not with optics. It's just they measure a gap which looks like an insulating gap in transport, and they apply a magnetic field, and the gap gets bigger.
Okay, thank you.
Yeah. There's also so-called 2+1 graphene, which is I take bilayer graphene and monolayer graphene and twist them relative to each other. And in this, there's an insulator at integer filling again, and what appears to be a superconductor, although there's some debate about this, at near integer filling. Moving on to a different family, which I will talk about today, the transition metal dichalcogenides, which are monolayer semiconductors. You can play the same game with them. You can twist 2 of them relative to each other. And in this, we've seen evidence for Mott insulator behavior at integer filling. We've seen evidence for superconductivity away from integer filling. And I'll show some evidence for quantum critical behavior at this metal insulator transition today. Again, within this twisted transition metal dichalcogenide family, a different member of this family, this is some beautiful optics experiments that show insulating states, not only at integer fillings, but at fractional fillings, all sorts of fractions. They've seen evidence for insulating states, which they associate with either charge density waves or Wigner crystals or things like that. So this is all, again, within the last year or 2, there's been sort of this explosion of phase diagrams that have been discovered in all of these twisted systems, which is why right now makes it interesting for us to study. Okay, so with this background, let me give you a few very recent results from my lab. And since it's going to be very recent, it might be a little rough, but that's fine. You can ask me questions. So I want to spend just a few minutes first talking about generically the band structure of these materials, and which feature these flat bands or peaks in the density of states, and where they come from generically and how we can manipulate them. And then I'll talk about 2 results, one of which is our recent observation of nematic behavior in twisted double bilayer graphene, and a second result, which is evidence for quantum critical behavior in twisted tungsten diselenide. Okay. Okay, so let's talk about the basic idea of flat bands, which is actually not a new idea and is something that we teach in our first solid state physics class. So imagine I take a two-dimensional semiconductor, and here I'm looking at the conduction band of the semiconductor. Then in 2 dimensions, it just has a constant density of states. If I imagine performing this twisting operation, which creates a long wavelength superlattice, then you know from basic solid state physics that if I apply a periodic potential to my band structure, that's going to create mini bands or subbands. And the position of these subbands in momentum space is the inverse of the real space wavelength. And as soon as you do something like this, my conduction band is going to break up into subbands. And each of these subbands is going to have a peak in the density of states that corresponds to one or more Van Hove singularities in the band structure. And so at its most basic level, this is all that there is to it. You apply a periodic potential to a two-dimensional band, and this periodic potential is going to create for me peaks in the density of states. And once again, because you can sort of tune the doping at will, you can enter one of these peaks in the density of states and asks what happens when you enter into those peaks. Okay, so if you now get into the details of individual materials, the details are slightly more complex than this and often can be very interesting. And so let me walk you through the most famous of these examples, which is the case of twisted bilayer graphene. So in graphene, you have the famous Dirac dispersion for a single layer. And if you follow exactly the same argument that I gave you on the last slide, then what this would say is once you have a periodic potential, then this periodic potential is going to open subbands in graphene, and these subbands are going to be spaced by the wavelength of your Moray superlattice. Now, something that Alan MacDonald and his student realized back in 2011 is if you have a real bilayer of graphene, I have 2 layers of graphene, in order to do the calculation properly, there's 2 effects going on. One effect is the fact that there is a superlattice, and the superlattice exists on each of the 2 layers. But the second effect is that electrons can hop back and forth between the 2 layers. And we all know how to handle that. If you have a 2-state system and electrons are hopping between the 2 states, then in general, you'll produce two and a bonding and anti-bonding orbital. And so when MacDonald and Bestritzer did this calculation properly, so this is the band structure coming from one of these 2 graphenes, and this is the band structure coming from the other graphene. And they're not sitting at the exact point because they're twisted with a small angle relative to each other. And then when you properly account for the fact that hopping can exist between the 2 layers, you find that you exactly at this point, you are going to produce bonding and anti-bonding states. And if you tune the angle exactly right, then one of these states they showed has this amazing property that it's perfectly flat in momentum space. So within this simple calculation, it was a band that has absolutely no dispersion, so it's perfectly flat. And this was sort of the motivation for many people to do their experiments to see if one can actually find this flat band structure. So the initial part of the experiments that I'm going to show you are all coming from STM. This is my one slide on STM for the uninitiated. So STM has a metal tip on top of a surface with tunneling happening between the tip and the surface. And the number of ways you can have tunneling between the tip and surface is proportional to the density of states, a number of available states at that particular point. So it's a good way of measuring the local density of states at a given point in space and at a given energy. So what we did is when these results came out is we started making these samples. And it turns out that these samples are a complete pain in the butt to make because you try to make a sample with a given angle and nature doesn't want to stick to that angle. It sends it off to some other angle. And roughly 1 in every 10 or 20 samples works, which is very annoying. But what this allows you to do is to get data on all kinds of other angles that you didn't really want to get, but happened in any case. So here is a typical example. This is twisted bilayer graphene. You can see the little dots of the individual graphene lattices, and this large superstructure that you see is the Moray pattern. In this case, this Moray pattern is 7 nanometers which corresponds to a twist angle of about 2 degrees. And I just want to make the point that you can see that the ratio between this Moiré pattern, which is 7 nanometers, and the lattice constant of graphene, which is 1/4 of a nanometer, is quite large. And so what this means is you need a very small number of electrons in real space to fill one of these bands completely. It's very easy to do. Okay. And so we went through and we made a bunch of these samples with different angles until eventually we hit this magic angle of 1.1 degrees that McDonald had predicted and where superconductivity had already been observed. And we were able to measure the spectrum of that particular sample. I don't want to take you through this since it's sort of old work. Just to say that the spectrum clearly showed 2 Van Hove singularities, exactly like McDonald had predicted. The energy spacing of these Van Hoves was not exactly what McDonald had predicted, but it was not a huge surprise in the sense that McDonald's calculation was a very simple calculation. What I want to show you from this data set is, again, how easy it is to dope this sample. So all we do in this experiment is we just apply a gate voltage while performing our STM experiments. And as you do this, you can see the chemical potential nicely shifting as a function of this gate voltage. And you can see that we can go precisely to 1/2 filling of this Moiré lattice, where you see a little insulating gap appear, exactly like transport had told us. And once again, this is just to say that it's really easy to sort of cycle through samples by applying these gate voltages in these materials. Now,
Abhay, sorry, this is Andrei Nevedomsky. May I ask you just a clarification question?
Yes,
so
please.
You pointed out the 2 Van Hove peaks and remarked that they're just as predicted in McDonald-Bistritzer. Yeah. I don't remember the paper by heart, but my recollection was that there was a single flat band, and the Van Hove singularities I thought mainly came from the chemical potential, where you would be at charge neutrality. Is that not right?
Yeah,
why do you have 2 peaks separated by a gap?
Right. So in the original work by McDonald, the prediction was precisely at the magic angle that you would have 2 Van Hoves that basically sit on top of each other. So they would form a single Van Hove, right? And then there's a gap to other higher subbands.
Exactly.
Right? But this was, this was within sort of nearest neighbor tight binding. And so there are many reasons why that would not be exactly true. And so the real spectrum at the magic angle, as measured by us and now other people, several other groups in STM, is that the separation between these 2 Van Hoves is not 0, but it's about 40 millivolts. That's the separation at the magic angle.
I see. But would it not be true, and I totally believe what you just said, but would it not be also true, people often estimate the widths of the peak itself being maybe 5 or 6 or whatever, 10 MeV, and then usually there is a gap up to what happens at the other bands that are sort of, the rest of the stuff that happens around the gamma point. And that, depending on the twist angle, changes, but, people hope that it's maybe 15 or 20 MeV, and therefore you have a well-separated bands. But now you're saying, oh, but there is another band that's 50 MeV below what's called 0 here, and then what?
Sorry, so let's say we are not precisely at the magic angle, right? So even within McDonald's calculation, you have 2 Van Hoves, and the spacing between those Van Hoves is very small. So in McDonald's calculation, at the angle where we are, that spacing is going to be much less than 1 millivolt, right? Now, the experimental finding is that it's not 1 millivolt, it's more like 40 millivolts. Does that make sense?
Right. Let me ask you a purely experimental question. If I ask you to show on this plot in terms of MeV, where is the charge neutrality, where is +4, and where is -4? I think this would help me.
Right. So charge neutrality in the absence of external doping would be exactly in between these 2 Van Hoves. So right here. Right? Or let's look at the theory. It always looks more beautiful. So it's right there, right in between.
Yep.
Yeah. And +4 and -4 would be out here at something like 50 MeV and -50 MeV.
Okay, perfect. That answers my question. Thank you, Andy.
And the reason that you're absolutely right, one expects to see a real gap between the first subband and the higher subbands. But in a spectroscopy experiment like this, you always have inelastic processes that obscure that gap unless that gap is really at the chemical potential. So there are people, not me, who have doped it exactly to the chemical potential, and then you can see that gap more clearly. Yeah.
Thank you.
Okay. Okay, so in this experiment, when we were doing this experiment, we happened to notice something interesting, which is the following. So if you measure at an arbitrary doping, you measure what the local density of states looks like, then you would notice that the local density of states looks approximately threefold rotational symmetric. And this is at different energies for a given value of doping. So at this particular value of doping, let's stick to this particular value of doping, which is charge neutrality. The local density of states looks approximately threefold symmetric, and it's the same pretty much for all energies at low energy. And I say approximately because in these samples at the time, so this was 2 years ago, there was always a small amount of strain that's present. And this strain always breaks the threefold rotational symmetry. But perhaps you'll still agree with me that, for example, here it looks pretty much threefold rotationally symmetric. And what we could do is we could change the doping by applying this gate voltage, and we brought it to this condition where you have precisely 1/2 filling of one of these Moret subbands. And when you did that, so this is that condition, doping condition, where we brought the chemical potential to exactly 1/2 filling, and you can see a little gap start to develop at the Fermi level. And at this particular condition, if you start to image what the local density of states looks like, we found, much to our surprise, that the threefold rotational symmetry is completely broken, right? And because of the fact that we could see this clearly as a function of doping within the same sample, we had some good amount of confidence that this was not just coming from external strain in the sample. It's something intrinsic. It goes away when you move the doping away from that particular value. Only when you're at this particular value, you see this threefold rotational symmetry breaking. And once you saw it, we saw this over a reasonably wide range of energies near the chemical potential. But at the time of that experiment, our samples were limited basically to a few unit cells. As you can see, this is sort of, 1, 2, 3, 4, 5, 6, 7, 8 or 10 unit cells, and was not all that satisfying. And there are other groups which also after us saw the same effect and published. All of the data kind of looks like this. So we decided to ask the question, how universal is this phenomenon in these kinds of graphitic systems? Is this something that's very specific to twisted bilayer graphene, or is this a common feature to other twisted graphene systems? And the one that we chose to work on is this system of twisted double bilayer graphene. And so once again, this is sort of the transport phenomenology of this particular system. At charge neutrality, and in the absence of an external electric field, the material is a semi-metal, it's conducting. And at exactly 1/2 filling, once you start to apply some electric field, you can drive it into an insulating state. So this is a material which has a slightly richer phenomenology than twisted graphene. You need that electric field to drive it into the insulating state. And as Peng-Cheng asked, this insulating state appears to be ferromagnetic in transport. So we did a bunch of STM experiments on this material, and we concentrated on electric fields that are quite small. So at all electric fields that we measured the sample is actually metallic. It's not insulating at any of these electric fields. But it's otherwise very much like the transport system. So in this sample, for technical reasons, which I can get into if somebody's interested, we were able to make beautifully clean and beautifully large samples on macroscopic, i.e. micron size length scales. So each of these dots here is not the atomic lattice. Each of these is one Moret unit cell, which is about 10 nanometers. And so you can see over sort of hundreds of Moret unit cells, we have a very uniform system. And if you calculate what the strain is just from looking at these Moret positions, the experimentally measured strain in our samples is basically 0 within error bars. So it's 0.05% plus or minus 0.05%. So we're able to make clean samples where strain is basically negligible. And so what we first showed is that in this system, exactly like twisted bilayer graphene, there are the same types of flat bands. So here you see these are flat bands that are present near the Fermi level. And then there's the next set of flat bands that are away, and then the various sub-bands as you go higher and higher up in energy. And we were able to actually use theory to sort of confirm exactly what we see in experiment to show that our spectroscopy matches what one expects for single particle theory, both by DFT and sort of analytical methods. And one really nice aspect of this system is that the local density of states, the wave functions of this material, are incredibly rich and complex. And so here I'm showing you wave functions or local density of states at different energies. And the top is experiment, the bottom is single particle theory. And you'll see, for example, these really nice, beautiful looking flower-like patterns. And why this is very important for us is that any amount of breaking of rotational symmetry becomes very obvious with these sorts of wave functions. So if you just have a dot, then it's difficult to tell if the dot is slightly elongated or not. But as soon as you have structures like this, which extend over the entire Moiré unit cell, you can easily tell if threefold rotational symmetry is broken. Okay, so this is a picture of the local density of states of this system exactly at charge neutrality. And at charge neutrality, no matter which energy you look at, you can see threefold rotational symmetry everywhere. Right? So now we play the usual game. We apply a gate voltage and we dope the system, and we ask what happens to all of these wave functions as you start to dope the system. And quite interestingly, we found that there is an entire range of doping where the threefold rotational symmetry, so this is near charge neutrality, where you can see over a large area, you can see the threefold rotational symmetry. And then this is close to, but not exactly at half filling. This is at 0.6 filling. You can see the local density of states, and it completely breaks this threefold rotational symmetry. So you can see nice lines that are elongated in one of the three principal directions. And so this was sort of our primary finding, is that this material has a nematic phase, and this nematic phase is not confined to a particular value of doping. It extends over a rather wide range of doping from about 0.3 to 0.7 filling of the Moiré unit cell. And importantly, it also exists when the system is not an insulator, when it's a metal. So very much like the case of the pnictides, where there's no real insulating state. This is a metal, and it exhibits this nematic behavior over a fairly large range of doping.
So this is purely electronic, right? I mean, there's no distortion of lattice that you can see.
Yeah, no distortion of lattice that we can see, and no evidence for any lattice distortion.
But why is it? I mean, which direction is this nematic phase? Why is it? Which direction is it locked to?
So it picks one of the three principal axis directions. And that's also an evidence for the fact that it's an intrinsic phase. It doesn't pick some random direction. It's always along. You can see here it picks this principal axis. What we would love to be able to see is domains of this nematic phase where it changes direction, like we could see in the pnictides. So far, we've been unable to see domains in these samples.
Do you have an idea why is it? I mean, prefer one particular direction? I mean, because if it's three directional rotational symmetric, you should expect all three directions to be equivalent, right?
Yes, but it's a spontaneously broken symmetry. So it picks one of the three directions, and one would expect that if one has an infinitely large sample with no external strain, that you should see all three domains.
Okay.
But we've never managed to see the domain structure in this.
Okay. Thank you.
So would it be correct to say that you're sitting at one place in the sample, let's say, and then as you could tune the gate voltage and see how the C3 symmetry first is preserved and then spontaneously broken?
That's exactly right. That's exactly right. So this is in fact in the same area of the sample.
Okay.
And you can see here, you can see nice, round things that look threefold symmetric, and here that threefold symmetry is broken. So everything is the same, disorder is the same, nothing else is changed. It's just the gate that's being changed.
Right. Now, purely theoretically, it would be very tempting for me to say, oh, well, it's just a charge density wave. Some people might say, oh, well, maybe it's like a Wigner crystal, but the point I'm trying to make, it's a spontaneously broken symmetry because as you try to put charge in the system, it tries to arrange itself in a way that would be self-avoiding to the best extent possible. And it decided to form a unidirectional charge density wave with a Q vector given by some periodicity. Would that be correct? Could one verify that?
No, so if you take, the Moray lattice forms a triangular lattice here. You can see this triangular lattice. And so if you were to characterize the Q of this state, it would be a Q equals 0 state. So you can see that every row of atoms is as bright as every other row of atoms.
I see.
So we don't see any Q, non-zero Q associated with this, which is why we would call this a nematic.
Okay. Thanks.
Abhay, in a twisted bilayer case, do you see some sort of variations in the orientations?
So the twisted bilayer, to be honest, the size over which we can get strain-free areas is so limited that I wouldn't be able to give you a good answer to that question. And
but you cannot look at different parts of the same sample and just see which way it's oriented.
It does, but the strain also varies significantly on that same length scale. And so it's very difficult to tell.
So the answer is not particularly meaningful in that case because of the strain.
That's right. That's right. And I don't think anybody has a good answer there as of now. Yeah.
And maybe just a follow-up to what Andrew asked. So the point is that you don't see charge density modulation in any way, right?
Yes.
Or can you tell?
Yeah, we should be able to tell. I mean, there's always an experimental question of how much is whether there's some subleading charge density wave also present, right? I suppose we could put a bound on how big the component would be.
Right.
We haven't tried to do that, but it would be small. Yeah.
Okay. Yeah. Thanks.
Well, maybe there is a little bit of nomenclature. I mean, I guess, Abhay, when you say charge density wave, you would like to see a Q vector which is not already present.
That's right. That's right.
From a purity point of view, if you see a ferromagnet, it's also intra-unit cell ordering, and yet it's spontaneously broken. So one could argue that what you see abundantly does look a charge density wave, which just its periodicity happens to be the same as that of Moray, and so it doesn't break any additional symmetry.
I guess, but I mean, from my experimental perspective, if I call the Moray lattice as my lattice, and if my order preserves that lattice, then the term charge density wave would somehow seem to be wrong, because it's like saying that a solid is a charge density wave, right? A solid is a charge density wave also, but
the experiment only sees the rotational symmetry breaking. That's the point.
That's right. No, okay. So experimentally, there's no additional Q vectors other than the Moray. Yeah. Okay, good. So that was actually really all I wanted to say about that particular system. And I want to jump over to this other flat band system, which we've been studying quite intensively. And this in many ways is actually simpler than twisted bilayer graphene. This is 2 layers of tungsten diselenide, which is a monolayer semiconductor. And all the action in tungsten diselenide happens in the valence band of tungsten diselenide. So the conduction band is sort of infinitely far away. So the complication of graphene is that it has this Dirac band structure, and you have both the conduction and valence band. In semiconductors like this, you only have to worry about one band, and so life is actually much easier. And as I said, once you introduce this Moray pattern and you have this periodicity that appears in the system, you're going to break the band structure up into subbands. And all of our physics is within the first subband of these Moray bands. So very simple system. And there are lots of beautiful works, but here as well, Alan MacDonald has a leading role in predicting lots of interesting physics in these systems. So, okay, so what we did is we made a sample of twisted tungsten diselenide, and then we do transport. So these are all transport measurements, nothing on STM just yet, although we have some preliminary data. And we do the same business that you do for graphene. You change the doping and you see what happens to the transport as a function of doping. And what we observed is, like twisted bilayer graphene, as you tune the density, and this is in units of filling of the Moray unit cell, As you go to half filling of the Moray unit cell, you observed an insulating state. So dark here means insulator, the dark red, and the blue here is metallic. And as you lower the temperature, then you entered an insulating state at fairly low temperature on the order of 10 Kelvin at precisely 1/2 filling, like twisted bilayer graphene. And here are shown a few of the actual traces of resistivity as a function of temperature, where you can see that if you're sitting exactly at half filling, then you go from something that's weakly metallic to insulating behavior with a fairly well-defined transition temperature. And if you're away from this half filling point, then you have metallic behavior all the way down to the lowest temperatures. And for particular angles under particular conditions, which I don't want to go into detail, but I'm happy to if you have questions, when you dope away from that insulating half-filled position, we were able to actually observe zero resistance, although we would like to see a few more samples of this before we say a lot more about it. The maximum TC, quite interestingly, was quite similar to twisted bilayer graphene, which is sort of an interesting phenomenon. Okay, so something very nice about this particular system is that you can use this electric field degree of tuning to actually tune the band structure. So here is sort of a cartoon picture of how that happens. As I apply this electric field, initially I have electrons that are present in both the layers, and both of these at the top of the valence band are degenerate. But once I start to apply this electric field, then there's an on-site potential energy difference between electrons in one layer versus the other layer. And so you can see that this is a nice way of tuning the actual band structure. And this is a busy slide. And all I want you to take away from this is perhaps this theory calculation, which says that as you apply different values of electric field, so these are the different colored curves, you can tune the density of states, you can tune the bandwidth by applying this electric field. And we were also able to show this experimentally that this is true. And what we found, this is again running a little fast, but let me just jump to the main point. As a function of electric field and density, we found that there is an insulating phase which exists over a range of electric fields and disappears for very small or very large electric field. So there's a metal to insulator transition. And so if I look in this as a function of electric field and density, there's a region of insulating behavior which is around 1/2 filling as a function of doping and within some bounds for the electric field. And one can ask, what does the transport behavior of a sample like this do as you sit at various points in this phase diagram and vary the temperature? And what we've discovered is that it's quite interesting, and I've been talking quite a bit with Chimiao as well about this. So let me show you some transport data which is taken along this particular line. It's a line of almost constant electric field, not exactly constant electric field, and it's sort of intersecting the region where the insulating phase is exactly the boundary. And what I'm going to show you is as you tune the density along this particular line, what does the resistance of the sample, the longitudinal resistance, do as a function of density? And if you sit at low temperature, what you'll recognize right down there is the insulating phase at half filling. This is an insulating phase at full filling, which is a simple band insulator. And as you raise the temperature, you'll see that the resistance actually changes quite interestingly as a function of temperature. And perhaps one of the really interesting aspects of this is that at high temperature of about 200 Kelvin, the resistance just saturates, becomes temperature independent. Now, you can go down to low temperature and you can look at the behavior of the resistance as a function of temperature and try to distinguish different regimes of behavior, whether it goes as T or T squared or whatever is the power of temperature. And so I'll show you here a few cuts taken at different values of doping. And let me point out what these cuts correspond to. If I sit beyond the band insulator, so this is some random place which is at very high doping, and you go down to low temperature, you'll find that the resistance as a function of temperature goes as T squared at low temperature. Now, this is coming closer to the half-filled insulator. So this is somewhere here between the band insulator and the half-filled insulator. if you measure resistance as a function of temperature, once again, you see nice T² behavior at lowest temperature. If you go to a special point, which is exactly at this metal or very close to this metal insulator transition as a function of doping, we find that the resistance is linear in temperature all the way down to the lowest temperature. And the lowest temperatures we've measured are down to 0.2 Kelvin, and it's linear all the way down to that temperature. Then exactly at 1/2 filling, if I sit exactly at 1/2 filling, at the lowest temperature, you see insulating behavior. So that's the insulating behavior that shows up. Above that metal to insulator transition here as a function of temperature, you see again a region of T-linear behavior, after which it starts to saturate. And if I go to the other side of doping, so now I'm going to the metal insulator transition on this side as a function of doping, once again, I see a particular point where R versus T looks linear in T all the way down to low temperature. And if I go even further, I'll see once again T² behavior emerge. So just on the basis of resistance as a function of temperature, we can break this temperature density phase diagram into the following behavior. And so let me get rid of the zoom. Okay, let me put this aside. Yeah, so this is this phase diagram showing you what the different types of behavior are observed. And you see something that is very reminiscent of quantum critical behavior. You see a region of T² behavior far away from this point. And this point is where T-linear behavior extends all the way down to T = 0. Then here there's a metal to insulator transition. Once again, a region of T-linear behavior. And to the right of that, once again, T² behavior emerges. And this T-linear behavior sort of goes out in like a very suggestive fan-like looking object, where if I sit, for example, at this doping and I raise the temperature, initially it's T², but as I raise the temperature, it goes over into T-linear before eventually going to saturation at high temperature. And
what are your units of N sub S?
This is in units of the Moiré filling. So 0.5 is 1/2 filling.
And when you say 1/2, because there are this double band, so I'm confused about the count. If you fill them completely, would you count that as 1 or as 2?
So if I fill it completely, it's 2 in this system.
Okay.
So in twisted bilayer graphene, it's 4 because there's an additional degeneracy. And in this system is actually simpler. So it's like a simple triangular lattice, and 2 electrons per site, per Moiré site, is full filling.
I see.
So yeah, go ahead.
But then NS = 1 or -1, wouldn't you call that half filling?
No, in this NS, okay, it's just a terminology. -1 corresponds to the full filling. I should have written 2 here. My students like -1.
Oh, I see. Okay, perfect.
They should have written 2, but it's not
sense.
NS. It's NS divided by
2, basically.
Yeah.
Okay, thank you.
Yeah. So for this quantum critical point, can you? Do you have any speculation from what phase to what phases?
Yeah, so this is, at this point, this is still speculation. We believe that the insulating phase is actually an antiferromagnetic insulator. And there is some speculation about whether there's actually some ferromagnetism in the metallic phase. And we are looking for signatures of anomalous Hall, and we have some signatures, but that's still not conclusive yet.
I see. Oh, so you mean these 2 quantum critical point may be 2 different magnetic phases. One is corresponding to anti, the other may be ferro.
But it's also a metal insulator transition. So it's also, yeah.
In the half-filled case, resistivity versus temperature doesn't say anything about whether there is a phase transition or not.
It does. So at exactly half filling, you'll see the resistance versus temperature suddenly start to rise below the phase transition temperature.
So that could also not just be the metal insulator transition, but also some sort of magnetic ordering. In principle, that's a possibility.
Yes. So we believe that. Okay. So at least okay. So this is within mean field theory. That's an antiferromagnetic insulator. So both would be simultaneous.
Yeah, whether it's simultaneous or not, it's a tricky question, but it's possible that signifying some magnetic ordering transition as well.
I see. So saying that the magnetism might onset perhaps before the.
Well, we see that in the bulk materials all the time.
Sure. Yes, that's certainly possible. Yeah.
Okay, good, very good. Thanks.
But if you believe there's a magnetism, that the resistivity goes up, metal insular transition. I mean, isn't MOT, you expect to have the gap opening at very, very high temperature? You not expect to see the.
Kenshi, you are jumping the gun, right? Yeah.
Yeah. So the experimental statement is that the gaps are quite small in this sample.
I see.
Yeah. So something that I learned from Chimiao is that if you look at the T-squared behavior, as you start to approach, let's just call this the quantum critical point, then one expects this coefficient of T-squared, which is related to the effective mass, to diverge. And I had my student, and he doesn't like to make nice plots, so I have to force him. So the nice plot hasn't emerged yet, but this shows you real raw data of what that coefficient of the T-squared behavior is. And you can really see that it enhances by a factor of more than something like 30 or 40 as you approach this quantum critical point. And similarly, as you approach it from the other side, as you come from here to here, also it enhances by similarly 20 or of that order. So really, it looks like, many of the beautiful experiments that were done in heavy fermions have a very nice parallel to the transport data here. One final or two final last things. We can change the size of the gap by applying this electric field, as I said. And if we do that, we find that the slope of the T-linear behavior is controlled by the size of the insulating gap. Again, telling you that this correlated behavior that gives rise to the gap at half filling is really the thing that's responsible also for the T-linear behavior. So this is the final thing about this, is we also observe, interestingly, linear in magnetic field dependence for small magnetic fields. And the slope of that linear in magnetic field behavior is actually maximized exactly where that critical point is. So another thing that has parallels to many of our favorite quantum materials. Okay, so I think I am at 1:59, so I have a whole other story, but let me save that for another day, where you can apply strain and see all sorts of things. Let me spend, shall I take one more minute before I quit?
Yeah, go for it.
Let me just say that, why is this, what can one imagine in the future? And I'll give you a rapid fire 1 minute thing of what one can expect. One obvious thing is to ask what other kinds of band structures can you make by this kind of twisting? So here, this is a pure theoretical prediction for a material called zirconium disulfide. If you do the calculation for this, you simulate that the simulated band structure looks very much like a Kagome band structure. We've already have some success in this direction. You can say, why stop at 2 layers or 3 layers or 4 layers? Why not make 50 layers and have electrons that are localized tightly in all 3 dimensions in space? And one can see things like the 3D quantum Hall effect, for example. So we've made some good progress in that direction. And all of these things that I've talked about so far are with fairly boring materials, in the sense that we started with graphene and a semiconductor, which are kind of the simplest things. One can play these same games with magnetic structures, where if I have 2 magnetic structures with cross ferromagnetic directions in the 2 layers, you can create Zaloshinsky-Moria type interactions. You can stabilize skyrmion phases, at least in theory, or Miron phases, and we're looking for these sorts of things. One can couple that to a superconductor and look at interactions between skyrmions and vortices. In theory land, life is very easy, maybe not so much in experiment. Let me jump over all of this. Let me spend now 10 seconds saying life is not always roses. Like with anything, we have disorder. Disorder is a killer. And there are 2 types of disorder. One is just point disorder, which every material suffers from. But perhaps equally importantly is, if you make a typical twisted bilayer, this is what your sample looks like. And so if you have a sample like this, then you can measure any transport you want on a sample like this. And so I think really getting rid of twist disorder or stretching disorder is a huge challenge in these materials. Okay, so I think I've taken up my time. Let me now just mention a few of the other people who've been key in this work. So Lede, Dante, and Martin are all theorists who were originally with Angel, but have now moved on to their own locations. The student of Corey's who worked a lot with me for the Twisted WSE2 is En Min, who's now at NIST. And Dan Rhodes grew fantastic samples for us, and he's now an assistant professor in Wisconsin. And okay, so with that, let me stop and take any further questions if you have any.
Thank you, Abhay, for your nice talk.
Thank you.
Any further questions or comments, Abhay?
May I ask a very quick one? Sorry, I don't know how to raise my hand here.
No, just
Go for it. Just
Abhay, you may have said this, and I'm sorry if I missed. Could you explain qualitatively why in a twisted double layer, or even in the case of tungsten diselenide, why exactly can you gap out the metallic state by applying electric field? What is the role that the electric field plays?
so let's work with the twisted WSE2. So okay, so this is, I can take you through that. Sorry. Oh boy. Okay. So in twisted WSE2, here's how we believe the argument goes. If you look at the band structure in the absence of this electric field, this band structure features a Van Hove singularity. And this Van Hove singularity is on one side of the half filling point. Right? And as you start to apply this electric field, then the Van Hove singularity actually moves through half filling. And eventually, for a very large electric field, it goes very far away from half filling. And the insulating state we observe in experiment is mostly in the region where the Van Hove singularity is going through half filling, right? And so our explanation for it is that, you know, it's a state that correlations are moderate, and you need the density of states to be high in order to realize the insulating state. Okay. Does that make sense?
Yeah, perfect.
Abhay, can I ask to follow up on that question? Hi, this is Ming.
Hi.
Thank you. So based on this band structure calculation on the left-hand side, does this mean that the field is tuning the Rashba splitting? So therefore, that's what is tuning the band structure?
That should happen also, but within this calculation, all that's happening is that there's an on-site potential difference. So let me take you through a little bit of detail of this. So the dashed line here is the valence band from one layer, and the solid line is the valence band from the other layer. And so you can see as you start to apply this electric field that the dashed line starts to come down and the solid line starts to go up. And so that's simply a potential difference between the two valence bands on the two layers. And this is the coupling between the two layers that, you know, the bonding and anti-bonding, that's this thing. But the primary effect here is simply the on-site potential difference between these two. Right? So the Rashba for these kinds of electric fields is small.
Can I ask if this is you have a top gate and a bottom gate? What is your approach for doing STM on this kind of a structure?
Very good question. So in STM, we don't have this luxury of the top gate. And in fact, that's bad in a certain way, because when you do an STM experiment, your STM itself is a top gate. And so when you're doing spectroscopy, for example, your top gate is also varying. And so this is right now, this is just a limitation of STM. You don't have this independent control. Now, interestingly, if you look at all the STM experiments, you put them together, you'll notice that some of them have very different values of electric field than others if you convert it. And I think what happens is with these tips, very often you'll have some insulating piece of junk that's very charged stuck to your tip. And this piece of junk is acting as a gate, right? And so it's not a reproducible way of doing anything, but if you do this 5 different times, you'll find different electric fields. And we're thinking about ways by which, you know, potentially if you have a gate which ends and you're sort of close to the gate, the field will still leak over and you can measure it. And we've done this for graphene, but the TMDs, not so far.
Yes.
Yeah.
Can I, sorry, just for, can I just one last question? So
Yeah, go for it.
Bilayer graphene, this kind of thing, how do you make the material ex situ and then put into your UHV or?
Great. Yeah. So we've progressed on that line as well. So with graphene, graphene is kind of like a gift, right? You can do whatever you want. You can spit on it and then you put it in UHV and everything is good. With the TMDs, you can, if you make your sample quickly in air and put it in, you can still do STM. There's work from us and few others on TMDs. Most of the other materials, you're a UHV person, you know that UHV is a real thing, right? It's not bogus. So we've now developed ways, there are two different things we've done. One is starting from a glove box, we can move it from nitrogen atmosphere directly into the STM without ever having to see other things. And now we're just finishing up a setup where we can do everything in UHV, true UHV. So exfoliation, finding, stacking, blah, 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 blah. When that happens, either I'll be very rich and famous or my students will be very annoyed with me, depending on whether it works or not. So,
Wow.
stay tuned. Yeah.
Any other questions or comments?
Yeah, Professor, I have
Yeah, go
also
for
a
it,
question.
Jimmy.
Yeah, Professor a very nice talk. I have actually 3 questions. The first one is you mentioned in the graphene talk, the region flag for the fading of from 0.3 to 0.7 actually has this kind of nematic phase rather than just one like single like a narrow area. The area is actually quite wide. So my question is, what any like a transport like signature between this wider range of area identified by the STM, with another like just a very narrow like single point or very small region? What's the difference?
Yeah,
in transport.
So, yeah, in transport. So if you look at twisted bilayer graphene, there is one work from Pablo, which is basically looking at in the superconducting state and looking at the anisotropy of HC2, which they find some anisotropy of HC2. So that's the transport evidence for nematic behavior. In twisted double bilayer graphene, there's no evidence so far, but we are actually trying to do experiments. So what you would want to do is to measure the resistance along the 2 different directions. And see how that changes. And in the ideal circumstance, you want to do something like the beautiful work of Ian Fisher, where you apply some strain and look at some response. So that's something that we are trying to do. But these things can be quite a delicate signature in transport, right?
Yes,
These guys are very special that way.
I see. Yeah. I kind of like know, for the WT2, although it's not like a graphene, such nice, beautiful, like C3 symmetric stuff. If you twist it, you can also form that kind of, line shape, this kind of transport. But then the implant anisotropy can change dramatically, actually.
I see.
The second question is for the WSE2. Sorry, I think I somehow missed the part. Which phase is this? 2H phase or 1T prime phase?
This is the 2H phase. So it's
so it's a semiconducting phase.
Yes. Yeah.
I see. So, but and you expect anything new for the 1T prime? I mean that 1T that will be already like a semi metallic phase.
So I don't know about WSE2. I don't know about the 1T prime phase, honestly, but
1T actually.
Or 1T. But in the related compound, which is tantalum selenide, there the 1T phase has this famous Star of David charge density wave. And there's a experiment recently from Micromi that claims to see evidence of spin liquid behavior and some scattering from a spin-on Fermi surface in a monolayer of 1T TaSe2. So yeah, the physics is quite different in those because those are metals.
Yeah, my final question is regarding building this kind of Marie Pant superlattice with magnetic monolayer or field layer. It has to be implant magnetic ordering, right? If it is, let's say if it's chromium triton, then there is no Marie pattern.
Great. Yeah, so there are in-plane magnets. So the one that we are working with quite a bit is called chromium sulfur bromine, CRSBr. That one is an in-plane magnet. And it has some beautiful optical properties as well. Now, one of the issues there with many of these materials is that with these dichalcogenides, the spin is on the transition metal. And so getting the out of plane exchange is actually quite small. Right? And so, to make it care about what's on top, you have to increase that out of plane exchange. So that still needs some work.
I see. Yeah. Thank you.
Yeah.
Okay, I think this is probably a natural point to stop. Thanks again, Abhay.
Thank you.